projects. In this video, we are going to explain about the project, which is PlantDet, a robust multimodal ensemble method based on deep learning for plant disease detection. Introduction of the project. The project recognizes the critical role of plants playing in sustaining life on Earth, emphasizing their significance as a primary food source for all living creatures, particularly humans. It underscores the economic importance of agriculture in regions like South Asia, where farming is a cornerstone of the economy. The project addresses the threats posed by plant diseases, especially in the context of staple crops like rice in Bangladesh. It highlights the various factors affecting plant growth, including diseases and the subsequent impact on food security due to the reduced crop yields. The project outlines prevalent diseases affecting rice and beetle leaves such as leaf blast, leaf blight, brown spot in rice plants, and healthy and not healthy in beetle plants. It underscores the economic losses incurred annually due to these diseases, emphasizing the need for early detection and effective control measures. The project discusses the historical challenges in plant disease detection, emphasizing the need for precise and quick diagnosis. It introduces the concept of deep learning as a transformative tool for computer vision based disease detection, acknowledging its capabilities. The project proposes a novel multimodal ensemble technique called PlantDet for identifying rice and beetle leaf diseases. It introduces key components of the model, including its basis on Inception ResNet v2, efficient net, and exception models. The contribution of the project, such as efficient data augmentation, pre-processing techniques, and optimization strategies, are highlighted, along with model superior performance compared to existing state-of-the-art models in both rice and beetle leaf datasets. Objective of the project. The primary objective of the project is to develop an advanced deep ensemble model, which is PlantDet, capable of accurately identifying and classifying the five most common rice leaf diseases, which are bacterial leaf blight, brown spot, leaf blast, leaf scale, and narrow brown spot, as well as distinguishing between healthy and unhealthy beetle leaf classes. The project aims to contribute to the early diagnosis of plant diseases, particularly in rice and beetle leaf crops. By detecting diseases at an early stage, farmers can promptly implement necessary measures to cure the disease, thereby enhancing agricultural efficiency and production rates. PlantDet is designed to overcome challenges related to underfitting and overfitting, which are common issues in the context of sparse datasets with a limited number of diverse background images. The objective is to create a robust model that maintains high performance levels even with the scarcity of training data. The project aims to improve the robustness and overall performance of the model by integrating various components, including efficient data augmentation, pre-processing techniques, global average pooling layer, dropout mechanism, L2 regularizers, p-relu activation function, batch normalization layers, and additional dense layers. This comprehensive approach contributes to the model's ability to handle diverse challenges in disease detection. The final objective is to thoroughly evaluate the performance of PlantDet using key metrics such as accuracy, precision, recall, and FN score, and the specificity. To implement the project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. In this step, necessary Python packages and libraries are imported into the project environment. We have imported NumPy and Pandas for data manipulation, TensorFlow and Keras for deep learning, PyTorch for image processing, Flask for web development, Matplotlib for visualization. Coming to exploring the dataset, this step involves examining the characteristics and the contents of the rice leaf data and beetle leaf data. Here we understand the dataset, which is crucial for making informed decisions during the subsequent steps such as data pre-processing and model building. Coming to image processing, this step involves utilizing the image data generator to augment the dataset through several transformations. Here the transformations include rescaling, which is adjusting image intensity values, shear transformation, which is changing the shape of the image, zooming is altering the image scale, horizontal flip is creating mirror images, reshaping is adjusting image dimensions. The next step is image processing with torch vision for detection. This step involves applying additional image processing using Torch Vision, a library for computer vision tasks. Specific enhancements and the transformations will be performed for tailoring detection tasks. The next step is building the model. This step involves defining the architecture of the deep learning models for both classification and detection. It includes defining layers, specifying connections, and configuring parameters to enable the model to learn from the provided dataset. Training the model. This step involves using the prepared dataset to train the model. During this process, the model learns to recognize patterns and relationships within the images, gradually improving its ability to make accurate predictions. The next step is Flask framework with SQLite for sign up and sign in. This step involves implementing a web framework Flask along with the database which is SQLite to manage user authentication. It enables users to sign up and sign in, providing a secure and personalized experience. User upload image for analysis. This step involves allowing users to upload images for analysis. It facilitates user interaction with the system, enabling them to submit images that they want to model to analyze. The next step is pre-processing given input. This step involves preparing the user uploaded image for model input. It involves resizing, normalizing, and applying other transformations to ensure compatibility with the model's expectations. The next step is using trained model for prediction. This step involves applying the trained model to predict the outcome based on the pre-processed user uploaded image. The model leverages the knowledge gained during the training phase to make predictions. The last step is final outcome is displayed. This step involves presenting the results of the model prediction to the user. It completes the user interaction loop, providing feedback on the analysis of the uploaded image. Now we will know what are the algorithms used in the project. The first algorithm is ResNet 101. It is a deep neural network architecture that belongs to the ResNet, which is residual network family. It is characterized by its use of residual learning blocks, allowing the training of very deep networks. It is employed for its ability to handle deep networks effectively. Its residual connections help mitigating the vanishing gradient problem, allowing the model to learn intricate features. Coming to DenseNet 201, it is a densely connected convolutional neural network architecture that maximizes feature reuse across layers. It uses dense blocks where each layer receives input from all preceding layers. It is utilized for its parameter efficiency and feature reuse, leading to effective learning. It helps in capturing intricate patterns and relationships within the dataset. The next algorithm is Inception ResNet V2. It combines the ideas of GoogleNet's Inception architecture with the residual learning concept. It is a deep convolutional neural network known for its efficiency in image classification tasks. It is chosen for its ability to capture complex features and its effectiveness in image-related tasks. The combination of Inception and ResNet principles enhances feature representation. Coming to ResNet 152, it is another variant of ResNet architecture. It utilizes deep residual networks to address the challenges of training very deep networks. It is employed for its ability to handle deep architectures, allowing the model to learn intricate patterns and representations in the dataset. VGG16. VGG refers to Visual Geometry Group. VGG16 is convolutional neural network architecture with 16 weight layers. It is known for its simplicity and uniform architecture, consisting of multiple 3x3 convolutional layers followed by max pooling layers. It is used for its straightforward architecture and effectiveness in learning hierarchical features, particularly in image classification tasks. Inception V3 is a deep convolutional neural network architecture that belongs to the Inception family. It is designed for efficient image recognition and classification. Inception V3 is chosen for its ability to capture diverse features using multiple filter sizes in parallel, making it effective for image-related tasks. Coming to exception, it is an extension of Inception architecture known for its depth-wise separable convolutions. It separates the spatial and channel-wise convolutions, reducing the number of parameters. It is utilized for its efficiency in learning hierarchical features and reducing computational complexity, making it suitable for resource-constrained environments. VGG19 is an extension of VGG16 with 19 weight layers. VGG16 is characterized by its simplicity and uniform architecture. VGG19 is employed for similar reasons as VGG16, providing a straightforward and effective architecture for feature learning. The next algorithm is EfficientNet V2L. It is a part of EfficientNet family known for balancing model efficiency and performance by scaling network dimensions uniformly. It is chosen for its efficiency in handling various datasets while maintaining the high performance. The next algorithm is EfficientNet B7. It is another variant of EfficientNet architecture designed for larger and more complex datasets. It balances model size and accuracy through the compound scaling. It is employed when dealing with more intricate datasets, offering a balance between model complexity and accuracy. Coming to CNN with PRELU, CNN with PRELU refers to convolutional neural network using parametric rectified linear units, which is PRELU, as activation functions. PRELU introduces learnable parameters in the activation function. PRELU activation functions are used for their ability to adaptively learn the optimal activation parameters, potentially improving the model's representation power. The next algorithm is CNN with PRELU and sigmoid. This variant includes sigmoid activation function in addition to PRELU in the convolutional neural network. Sigmoid is often used for binary classification tasks. This combination of PRELU and sigmoid is employed for specific tasks such as binary classification, leveraging the benefits of both activation functions. The next algorithm is DenseNet 201 with exception and with inception v3. This ensemble model combines DenseNet 201 exception and inception v3. Ensemble models utilize multiple base models to improve the overall predictive performance. The combination of diverse architectures enhances the model's ability to capture different aspects of the data, potentially improving overall accuracy and robustness. The next algorithm is EfficientNet V2L, DenseNet 201, and VGG19. This is another ensemble model. This combines EfficientNet V2L, DenseNet 201, and VGG19 architectures. This ensemble models leverage the strengths of individual architectures, potentially leading to improved performance, especially when dealing with diverse datasets. The last algorithm is Inception ResNet V2 with EfficientNet V2 and with exception. This is PlantDet. It is multi-model ensemble technique integrating Inception ResNet V2, EfficientNet V2, and exception architectures. This ensemble approach enhances models' robustness, improving predictive performance through diverse features representation, and effectively addressing challenges such as underfitting and overfitting in the context of rice and beetle leaf disease detection. PlantDet's combination of state-of-the-art models aims to provide a comprehensive and adaptable solution for accurate plant disease identification. As an extension, we have further enhanced the performance by exploring other techniques of Euler family for detection of the disease. And also as an extension, we built the front end using Flask framework for user testing with the user authentication. We have used accuracy, precision, recall, and FN score to evaluate the classification models of the project. So here we have the comparison graphs for the classification of beetle leaf dataset. First, we will know what is classification. Classification is a machine learning task where the goal is to assign predefined labels to the input data based on its features. For example, in an image classification, the model learns to categorize images into specific classes such as recognizing whether an image contains cat or a dog. So here we have the comparison graphs for classification models. This is accuracy comparison graph. X-axis represents accuracy score for each algorithm and on y-axis we have algorithm names. Similarly, we will have for other graphs also. Accuracy measures the overall correctness of the model by calculating the ratio of predicted instances to the total instances. This is precision score comparison graph. It evaluates the accuracy of positive predictions made by the model. It is the ratio of correctly predicted positive instances to the total instances predicted as positive. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It measures the ability of the model to capture all positive instances. It is the ratio of correctly predicted positive instances to the total actual positive instances. This is FN score comparison graph. It is the harmonic mean of precision and recall. It provides a balance between precision and recall, and it is particularly useful when there is an imbalance in the class distribution. Here we have comparison graphs for classification of rice leaf dataset. Here we have comparison graphs for the detection of beetle leaf data. First, we will know what is detection. Object detection involves identifying and locating multiple objects within an image or the video, providing both categorization and spatial information. It goes beyond classification by outlining the position of objects within bounding boxes commonly used in applications like image-based security systems or autonomous vehicles. So here we have precision score comparison graph. This is recall score comparison graph and this is map score. MAP is mean average precision. Mean average precision is a popular metric for object detection that considers both precision and recall at different IOU, which is intersection over union thresholds. It averages precision values across different IOU thresholds and computes the mean. So here we have comparison graph for detection of rice leaf data. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the beetle leaf dataset and this is rice leaf dataset. We use these two datasets for training the algorithms. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap files. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. And these are the model files which contain the algorithm information and that will be loaded into the project code during runtime. And these two are the IPYNB files. These are the Jupyter Notebook files which contain a combination of code and graphs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. This will change current directory to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host, and the port, unless configured differently. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. So here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. So here we can see a sign up link. First, we need to click on that. Here we need to enter all the sign up details if we are signing up newly. I have already signed up and I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password to log in. And now we need to click on sign in. We have signed in successfully and we are redirected to prediction page. Now we will be doing the classification and detection of rice leaf disease and beetle leaf disease. First, we will do the classification of rice leaf disease. For that, under rice leaf, click on classification. Here we can see a choose file button. We need to click on that for uploading the rice leaf images. So I'm clicking on choose file button. From the rice leaf images folder, I'm selecting the first rice leaf image. Click on open. And now we can see that image has been loaded. Now click on upload. Here we can see that it has predicted as bacterial leaf blight, which means the rice leaf is suffering from the disease which is bacterial leaf blight. Now we will try giving the other image. Click on try again. Click on choose file. I'm selecting this image. Click on open and now click on upload. So here it has predicted as brown spot, which means rice leaf is suffering from brown spot disease. Now click on try again. Click on choose file. I'm selecting this image. Click on open and now click on upload. Here we got the prediction as healthy, which means rice leaf is healthy. Now we will do the detection of rice leaf disease. For that, under rice leaf, click on detection. Here, similar to classification, we can see a choose file button for uploading the images. So I'm clicking on choose file button. From the folder, I'm selecting this image for detection. Click on open and now click on upload. So here we can see that application has detected the DCs and it has drawn bounding box around the DCs and it has classified as narrow bound and it has given a probability score for that. Probability score of detection represents the model's confidence level in accurate identifying an object in an image. Now we will upload one more image. Click on back arrow. Click on choose file. I'm selecting this image. Now click on open and now click on upload. So here we can see that application has detected the DCs and it has drawn bounding box around the DCs and it has named it as leaf scale and it has given a probability score. Now we will do classification of beetle leaf disease. For that, click on back arrow. So now under beetle leaf, click on classification. Here we can see a choose file button. We need to click on that. Now we will upload images from the other folder, which is beetle leaf disease. I'm selecting the first image. Click on open and now click on upload. So here we got the prediction as unhealthy beetle leaf, which means beetle leaf is suffering from the disease. Now we will try with the other image. Click on try again. Click on choose file. I'm selecting this image. Click on open and now click on upload. So here we got the prediction as healthy beetle leaf, which means beetle leaf is healthy. Now we will do the detection of beetle leaf disease. For that, under beetle leaf, we need to select detection. Here we can see a choose file button. We need to click on that. I'm selecting the second image. Now click on open and now click on upload. So here we can see that application has drawn bounding box around the DCs and it has detected the DCs as unhealthy and it has given a probability score for that. Now click on back arrow. Now click on sign out. In this way, if we upload the images to the system, then the system will detect the DCs. Conclusion of the project. The multi-model ensemble PlantDet integrating Inception ResNet v2, EfficientNet v2L and Exception demonstrated enhanced capabilities in accurately identifying diseases in rice and beetle leaf datasets. PlantDet outperformed previous models, showcasing superior metrics for disease detection. Its robust performance underscores its efficacy in handling complex agricultural datasets. This ensemble's diverse architecture integration addressed challenges of underfitting and overfitting, ensuring adaptability to varied dataset characteristics and contributing to a more robust model. This project benefits farmers and the agricultural industry by providing a reliable tool for disease detection, leading to improved crop management and increased yields. The project incorporated a user-friendly interface through the Flask framework and SQLite for sign-up and sign-in functionalities. This streamlined user interaction, allowing users to easily upload images for analysis, enhancing accessibility and usability in real-world scenarios.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.